The following is a conversation with Steve Kautsch. He is a teaching professor in the physics department at Northeastern. His research focuses on mass distribution in the universe, dark energy, dark matter, and the evolution of planets. It is a common misconception that LEGO is for kids, but his clever use of them in his research proves otherwise. He also believes that LEGOs can be implemented in classroom settings, pushing the boundaries of modern education. Here is Steve Kautsch.
For us to...
Yeah, thanking Mark and Krish. Thank you for having me here. I hope I can answer your questions.
Yeah. All right. Shall we begin, I guess?
Sounds good.
All right.
Can you speak about your research? And also, you used the implementation of Legos relative to the universe. How did that process come of thinking that you could relate Legos to the universe and mass distribution?
Well, it didn't start with Lego. I wish it would, that I started first with Lego and then came into research. No, it was the opposite way. Because the whole problem, the whole idea was to show how things work with Lego, but that was not the additional idea. It started first that a colleague of mine, Dimitri, colleague and friend, and he's now in England at the University of Warwick, Dimitri Veras. He's there an astrophysics professor, and he asked me if we can do a little bit some research together about the number of planets in the Milky Way galaxies, how many planets are in the Milky Way galaxy. So it started off with some totally different idea that it developed into. But that number of planets depends on a couple of factors, a couple of speculations even, a couple of assumptions. But one of the most important things is the question, can have all stars planets? Because in the Milky Way galaxy we have massive stars which shine very bright, and we have a lot of low mass stars, almost like the sun, which do not shine as bright and are not as hot. And then we have even more very faint, small and low mass stars. So the idea was to bring that into the estimation of number of planets by finding out how many planets can have those massive stars and how many planets can have those small stars. So that was the initial idea. We have to do some more research about the initial mass function. That is how astrophysicists call that distribution of masses of stars. And then I thought to myself, not again mass functions, because I was working with the mass function already in the past a couple of times, one time with unresolved stellar population in the Milky Way and another time with mass function of galaxies. But I never really was into that, doing that again, because I was thinking that's like an old topic and nobody has to do that one more time because there are already so many studies about that. But then I realized when I talked to my own students about that at my previous university in Florida, that didn't really understand what is that mass function and the mass function of stars. Mm-hmm. So I had to come up with some idea to show that concept in very simple ways, because sometimes, or more than often, you have the case that students, like in our ILSs, we know all kinds of equations, but we really do need to understand what they really mean. Like we had the example with force, where people know all those equations with force, but nobody really knows what is the meaning of force. And remember, we said the meaning of force is something that you need in order to move something. Or in detail, you can say, okay, accelerate objects with masses, but that means only moving objects. And so the same thing with mass functions. Everybody knows those equations in my field, of course, not everybody outside, but not so many people have a deep understanding what really mass functions are, and they are so simple. Do you want to hear how it works with mass functions?
Let's hear it.
Yeah, one moment. Let me get to that, because when I was walking to this building from my building, the Dana Science Research Building with the physics department, I was thinking about, well, how should I explain it again and again? But the thing is, I was talking about the stars in the Milky Way galaxy. In the Milky Way galaxy, we have a couple of 100 billion stars. And there's only a very small fraction of massive stars that have a lot of mass and shine bright. Mm-hmm. There are many more stars like the Sun, which are somewhere in between. They are not as massive and not as low massive as those little stars. And there are many of those sun-like stars, but what's the most common type of stars are those stars with little masses that don't shine too bright, and you need really big telescopes to actually see them because they are so faint intrinsically, not because they are far away, but because they are here. And that is the mass function. It's simply the number of stars within a given mass range, and plotting that in a diagram. And the interesting part why I wanted to do that with LEGO is, well, first of all, I wanted to explain it to other people. But the other thing is, I realized that mass functions are much more common in other fields of science, and much more common in the universe than just for stars. There was this paper published in the 2000s, and that was determining that mass function not just for stars, but also for planets, planetary bodies. And they also found out that, for example, there is a lot more small stone-size microasteroids in our solar system than big planets like Jupiter. So there is the same thing. You have a lot more of the small stuff that doesn't weigh a lot, and you have very few big things. And they expanded that study not just for planetary bodies. They included nebulas, which are gas and dust clouds in the Milky Way galaxy, and they also found out there are a lot more of the smaller, low-mass nebulas compared to the big ones. And the same with galaxies. For example, our Milky Way galaxy is quite a massive, big galaxy, but there are many more smaller galaxies with lower masses and much less stars in them.
Can you speak more about why this occurs? Because with stars, lower mass stars have a longer life, right? So they last a lot longer.
Yeah.
But how is this also true for like galaxies and so many different like areas in space?
Oh yeah, if I would know that, that's the big question.
Okay.
Yeah, because I did some research then about that. So it's not only for celestial bodies, that distribution. It can be also found in a lot more things where you would not expect it. And a typical example related to astronomy is, for example, meteor crater sizes on the moon. Meteor crater sizes on the moon, there is only a couple of huge meteor craters on the moon that you can even see with the naked eye, but there are a lot of small meteor sizes. The other things are typically geological features like that, follow all the same distribution, like river sizes. We have just one or two massive rivers in America, which is that Mississippi-Missouri River. But we have a lot of small rivers, like here the Charles River, but shorter. So there is that kind of feature everywhere, but not just in nature. And that's the interesting thing. Mm-hmm. It's not just in nature, it's also in the biological nature. When you think about mammals, the most massive mammals, I think these are those whales, There are different types of whales, but they are all pretty massive and large. And elephants. But when you compare it to other mammals, there are a lot more of mice and rabbits and rats and other small mammals. And I think that's not just for the mammals, it's like for almost every other type of animals around. And also for the nature. Here on campus, maybe that's not a good example because it's maybe artificially altered. But when you think about nature in general, we have a lot of trees on Earth, but those massive trees are very rare. What is the name of those? The mammoth trees? I forgot. The ones in California. These are the most massive trees, and then you have a lot more of smaller trees, but you have even more bushes. And then when you count the number of grass plants here, you have a lot more of them.
So this seems to be like a pretty consistent trend, not only in the universe, but on Earth as well.
But here on Earth as well, and even artificial things are like that. Because when I walked here again, I looked around me and I saw a few of those skyscrapers in Boston, like the Prudential Tower. And also here it looks like we have in Boston, in the city of Boston, or in the metro area of Boston, we have only a handful of skyscrapers. We have a few more high-rise buildings, and then a lot more of single-family homes if you include the Newton and Malden and Everett areas and those things. So it's some sort of natural law that you see everywhere, and even in Lego sets. That's the thing. Because I was thinking I should do that with my student. He just got with his younger brother a Lego set from Lego Ninjago. Do you know Lego Ninjago?
Yeah.
Okay, yeah, that's
it's a good TV show.
TV show and Lego, and he brought that in, and I said, well, why don't we just measure the mass of each brick and see how they are distributed, that frequency mass distribution of the bricks. And we found out it's the same distribution. And not only qualitatively, it's even quantitatively the same. Because in astronomy, the ratio or the fraction of high to low mass stars always stays the same. Even the ratio of high to low mass star objects, not just stars, also between other celestial objects, is the same. It's this slope number 2 or -2. If you take the minus in front of it, it depends how you plot it. And even in the Lego set is the same thing. I brought one. I can show you a little bit how it is.
Perfect. Sounds good. And also, could you explain a little bit more about how it was related to the force of gravity, like the two? I saw that on your paper, and that was interesting as well.
Yeah.
That correlation.
So here is what I found at home. I have that since a couple of years unopened, but I can show you in that Lego set. It's actually 3 parts of it. It's called the Women of NASA, and just if you look at that one, that is a representation of Margaret Hamilton. She was a NASA engineer and did a lot of computation, but that's not really the topic here. The topic is here when you look at that set, and there are the bricks, the parts, the Lego parts. There are only a few big ones, that means massive parts, like here that base plate, and maybe this one, and maybe one or two of the slopes. But then when you continue, you see there is a lot of smaller pieces like that one, which has masses somewhere in between. And then, of course, even more low mass pieces, like those little pieces that represents books or tiles here in the background. So it's the same thing, and I almost bet if you do the mass function of that little Lego set, you will get the same distribution and not just qualitatively, but also quantitatively.
Wow.
So
Fascinating
it's a
stuff.
very nice set. I'm very glad I had that. It is retired. You don't get that anymore in the Lego store.
Very fitting for today's conversation.
Yeah. Well,
Human
of
and-
course, the larger your sample is, the better is the
more precise
results.
Yeah.
Right.
So that might not be statistically significant, but if you get one of those larger Lego sets, and I think one of the largest is like the UCS Millennium Falcon
Oh,
or
yeah,
something,
like Star Wars,
or yeah,
Yeah, things like
then that's maybe more representative.
And do you think this sort of like distribution is caused because of there's a limited amount of resources? Because just based on what you describe of like everything from the universe, like to Legos, it seems like they all have this cap of like this is the maximum amount of things that we have. Like for example, in Lego case, it's plastic, and we're using this amount of plastic, and we're trying to build all these type of things, and we need smaller parts to have a more complexities of like, you know, maybe this joint can be used in thousands of other sets if it is small, but if it's a huge part, it's hard for you to integrate that into different systems. Do you think that's one of the reasons?
Yeah, I think it has to do with that, because one of the major theories that I mentioned also in the paper that I did is someone who does that a lot, and that's where I got the information about all the geographic features they have. That also in social sciences, in economics, you see that distribution, the same distribution is the Pareto and Gini coefficient, the distribution of wealth. It might be different in different nations, but in general there are only a few very rich people and a lot of much poorer people, unfortunately. But that is something almost natural, and he says that some sort of self-organizing power of systems and matter that follows that. But it really doesn't say why that happens. Like you said, it's like a self-organization, because you have to build things, and without organizing, you get a few more small pieces instead of just two big pieces to model something or to build something. That's like an organizational thing that comes from what you have, and therefore you have to organize it in that way. But in depth, it doesn't. I believe it doesn't really explain everything, because it just tells you it is what it is. It is what it is. But here's the thing. That's, according to my understanding, what I'm reading in my physics textbooks, also the one that we are using. Physics is here to show how things work, like what's the distribution, but not really why things work. So what I can do is just speculation and refer to my sources, to what I have. But you were asking about gravitation. If gravitation has to do that, can explain that for objects in space, not necessarily here in the city or for Lego bricks, but in space. And that's right, because one of the major properties of matter is mass, and masses interact with the help of gravitational force. The gravitation makes masses move. Well, there are other forces that can make masses move, like electromagnetic forces, but for long distances, it's gravitation. So it has to do with that, and that was already known. But how it really works, how to show that, how to simulate that, that's just the beginning of that research. And I hope I can contribute to that a little bit more from here.
You also talked about a little bit about your research about like the school system and how we learn how to do it, but not necessarily why. So do you believe like that Legos in the schooling system could help explain that why of why we do what we're learning?
I hope it helps. I think it helps at least to some extent, and I think it helps to more extent that some people realize, because I believe learning things is better when you do it learning by doing instead of learning just theoretically. So if you have something even in a physics course that you can touch, or at least you can see directly with your eyes, that relates you better to the formulas, to the equations, instead of when you just see an equation like force is mass times acceleration, the basic force equation. You see that okay, there is a mass and acceleration, that is force, but you don't really know what that means. So I try to make it visual, to visualize it, and here Lego can help.
And often like physics and space is so counterintuitive, right?
Yeah, sometimes it is. Yeah, I do agree with that, and then it helps. Like tomorrow we have another session, and it's a lot about sound waves, and their equation for that. And when you just see the equation, I think it's better to also have something in hand. So I found an demonstration object. Unfortunately, in physics, we have a lot of demos and experiments, but these are really classical, traditional experiments that have been shown to students since maybe hundreds of years, always the same experiment, and don't reflect much of reality in the real world anymore. So, or there are so specialized experiments that you don't see much often in nature. So I prefer something really to show students from daily life. And it seems Lego is popular, so why not Lego? And I used that the first time in my in that paper. It was really just an idea. I was thinking about the mass distribution. I know already you can see it not just in stars but in many other fields, and then somehow that Lego idea popped up. I think that's creativity that sometimes appears.
Yeah, because that, to me, I feel like there's so many theories, there's so many like just ideas that you don't know how people just come up with, and I feel like Lego with space is like one of those. It's like,
Yeah.
wow, that is a very big jump.
Yeah, while we're speaking about other things that doesn't necessarily come to our mind, you also research dark energy and dark matter to some extent?
Yeah, well, since I talk about distribution of mass and also dark matter has mass, so actually what that previous research paper that really digged into that problem of mass functions, universal mass functions, they also found out that those dark matter halos follow the same distribution like everything else, like the Lego set here. They follow the same distribution. I would be very interested to know the nature of dark matter and dark energies. Simply, what is dark energy? What is dark matter? But that's one of the. That is the. These are the biggest mysteries in modern physical research.
Can you speak a little bit about what dark matter and dark energy is?
So dark matter, which that was discovered probably 60 to 80 years ago by American scientists.
Just to clarify, it was first theorized 60 to 80 years ago. The actual discovery of it was more recent, right? Like the past few decades?
No, that is dark energy.
That's
the
dark
one
energy, okay.
that has been discovered by, I think there was Vera Rubin who had discovered that galaxies have much more mass than we actually see, and Fritz Zwicky, who discovered that also galaxy clusters contain much more mass than the galaxies that we actually see. So these two researchers that took a very simple method, they compared the mass of the stars in a galaxy. They just imagine you have a galaxy that consists of 10 stars only, and you know how many kilos has a star on average. We can determine that. That's not a big problem. So when you have 10 stars and you know each star has an average of 1 kilogram, that galaxy is supposed to have a mass of 10 kilograms because it has 10 stars. And it doesn't matter if the stars have a few planets, because that's minimal. And if it's one or two of those stars are black holes, there is the same mass. So that includes already black holes and everything else. And then you take that 10-star galaxy and put it on a scale, and you see it suddenly has 100 kilograms. That's the problem. That's the major problem in physics, in astrophysics. That's the dark matter. That missing 90 kilo is dark matter. We can measure it's there. We can measure it very easily with a lot of different independent methods. So you can measure dark matter independently, various ways. And you always come to that 100 kilogram galaxy. But when you actually sum up all the stuff that you see, then you only get 10 kilograms.
So they believe that the matter is there, but we just can't see it, and we can't fully understand what it is.
Yeah, we actually know the matter is there. There are a couple of theories in the past, but they all have to, they all were proven wrong, unfortunately. And even those modern searches for massive particles that are particles even more obscure than neutrinos that are here, have a huge mass, but don't interact with us. So they don't shine, they won't get absorbed, and they travel through our bodies and through our whole planetary system, even whole galaxies, without any interaction. But even those haven't been found with very sophisticated methods yet. And in the past there were other theories that also have been proven wrong, and they didn't find any of those candidates.
There was an interesting theory I read that dark matter is just ordinary matter from another universe, like the multiverse theory, and that could be a possible explanation for it as well. But that was just interesting to read, just thinking about that, right?
Yeah, that multiverse stuff. I know there are some astronomers or theoretical physicists working with that. It's highly complicated, very complex calculations. But here is the thing: in modern science, we say a good theory is something that makes sense theoretically. So you can calculate stuff, you can predict stuff, but you can also observe it. You can make observations. And with all those theories about multiple universes, you cannot observe that. People are looking for those observations. They look in the microwave background of the universe. That's like the noise that comes from all directions, not noise, but electromagnetic radiation. That's like the afterglow of the Big Bang. And they looked into asymmetries of that, and they didn't find anything. So there are no hints for multiple universes yet.
Interesting. And that cosmic radiation that you just mentioned, that was what allowed astronomers to realize that the universe is in fact expanding and not just steady, like it was thought in previously, like with this steady theory, if I'm not mistaken. So can you speak more about that, and also dark energy, which allows it to accelerate? Because that's counterintuitive. Because when we think of gravity, right, we think of it coming together, right?
Yeah, the dark energy, that's another thing. It has been observed that the universe expands. We can observe that also independently. The expansion of the universe has been discovered by Hubble and his team. Hugh Mason was one of those, and a couple of other people worked with that as well. And they discovered that the space between galaxies is expanding, and therefore it seems as if galaxies are speeding up the further they are away from us. And it has been recognized that the universe is expanding, but in the recent years, in the last 20 years, I think it has been also discovered that the universe is actually even faster expanding, is accelerating. The expansion is accelerating than we would have theorized before. And where that push for an additional expansion comes from, that must be some sort of force, because expansion has to do with force, and when you want to apply a force, you need to have energy. So there must be some sort of energy that allows that push force that pushes the space apart. There must be something like that energy, and because we know it's here, but it's invisible, it's called dark energy. But some astronomers like to prefer the name vacuum energy because it's in the space between stuff that makes it expand. So it's an energy that's in the vacuum.
And these galaxies were going away from each other, but like the Andromeda galaxy and some other galaxies nearby to us, in fact, like we're going to collide with it sometime in the faraway future, right? So
yeah, that's right.
So how does that work?
Yeah, because, well, it's actually not the galaxies that going away from each other. It's the space that pushes them apart. Right. But in some cases, when systems are gravitationally bound, then they still are attracted to each other and not pushed apart by the space expansion. And that's why we will collide with Andromeda galaxy and have our first encounter probably in about 3 billion years, because the Andromeda galaxy is really very close. It's not the closest galaxy. It's not the closest galaxy to our Milky Way. We have much closer ones, even some galaxies that are currently falling into our galaxy, like Sagittarius and a couple of others, those small galaxies or satellite galaxies, but it's the next big galaxy neighbor that we have. Yeah, and because it's so close, we are connected gravitationally, and therefore they spiral around and have an encounter in 3 billion years.
So when they do collide, what will happen to us, hypothetically, if we were to still be here?
Yeah, in 3 billion years, there could be still life on Earth. There is no reason why not. And nothing really would happen. We would just see more stars in the sky. Yeah, we would have a nice view, because we see a lot more things going on, maybe star formation and other brighter nebulas around us. But the stars won't collide because they are elastic, so they move around each other instead of colliding head on. That's because stars are considered elastic objects, so they won't collide, and there is so much space in between the stars, so even that interaction probably are almost non-existent.
I don't know if it's theorized or if it's verified, but there's a black hole in the center of every galaxy, correct? So like when both galaxies converge together, wouldn't the black holes merge as well to become one? Or
Yes, those supermassive black holes in the center of galaxies is another discovery that is not that old, and it also got the Nobel Prize in physics, like the expansion of the universe, but not the mass function yet. So
there's still time.
indeed, yeah. Well, in 3 billion years we have the first encounter, but the whole merging of those two galaxies together happens in about depends on what paper you're reading, but I think a good prediction is in about 5 billion years. And what happens then is that the two supermassive black holes, the one that we have in our Milky Way galaxy, which has been pretty much studied very well, and the one in Andromeda, they will also merge into one even bigger supermassive black hole. That's the case. It will probably send out some gravitational waves, like the whole thing will have some gravitational things, but I think it doesn't have too much. There's nothing really to worry about that, because at that time, in 5 billion years, that's where our future people here on Earth should start thinking about an evacuation plan from Earth, or better, actually take the Earth and move it somewhere else, because in about 5 billion years, the sun will get crazy and develop into a red giant star. And that's where when we have a problem, because then the sun's surface is right here on Earth. So we gotta have to move further away in order to protect ourselves. But theoretically, moving planets around is pretty easy.
Oh, really?
It is, yeah.
Can you expand on that?
Well, that's something that I hope has been taught in Physics 1.
Moving stars, moving planets.
Well, maybe not that example, but the equations that you need for that that have to do with that rotational motion and forces. I think that was in that
Yes.
semester. I gotta have to look up that semester because I'm new at this university. I never taught that class, but in the Physics 1 that I taught, you know all the equations that you need to move planets around. So what you simply need some sort of gravitational tractor beam to pull the Earth from its current orbit. And how you do that, it sounds very Star Trek-like, but it's not. You just need to push the moon in a certain direction and the Earth will follow it. That's the gravitational pull or tractor beam.
Yeah.
I think they did try that, moving objects with the help of gravitation in space. They tried it a couple of times. For example, in the DART mission with the little spaceship from NASA that
asteroids.
flew with an ion engine and flew to that asteroid, and they shot something on that and hoped to push the asteroid a little bit away from its current orbit. So that's one example. And there was I think a Japanese experiment doing something similar, but that's an older satellite that tried that, and they accomplished that. Yeah, so you can move stuff around with the help of forces, and if you have enough money and enough engineers, then you can move whole planets around. It's actually probably the worst planet-killing weapon if you abuse that power that you would have, because what you have to do is simply, here's the Earth orbiting the sun, and you have to stop. You have to manipulate the angular momentum of that system. You have to stop the Earth. Then it doesn't have any more that angular momentum and would spiral in or directly fall in if you really make it stop to be at rest relative to the sun.
But the
Then it
energy
falls in.
requires will probably destroy the planet, no? Or
And then you would destroy the planet because it falls into the sun. But planets don't fall into suns or black holes because they have an angular momentum, and the conservation of angular momentum tells us that that
Physics
doesn't
don't.
happen. And if a planet gets closer to the main mass, like the central star, the host star, the mother star, then it moves faster. That's why we have Kepler's laws. But if you want to destroy a planet, you just gotta have to make that planet moving a little bit slower and keep decelerating the planet, and then it would fall in the mother star and everything gets destroyed.
Dangerous information to know. Dangerous information to know.
It is dangerous, but every
it's
physicist know that.
Yeah.
Every astronomer knows that.
Yeah, so I feel like there's the knowledge of physics. It feels like we can do so much, like theoretical stuff. Like we can destroy stars, we can move planets. But when we go to the real world and becoming an engineering problem, it becomes so much more complex. And just like thinking about how, like the current scale of like we're still sending people with rockets, and to compare it to like the theoretical world where we can like, manipulate stars, manipulate black holes, and all of that. It feels like there's this huge gap in the exploration fields and kind of the application fields. And do you think we can someday catch up, having the ability to do those stuff?
I think it's first of all it's very good that we have already the intellectual knowledge about that we know what is possible, that we have the theories, and we understand the facts, and to get to a technical level, to an application level where we can do all those things is probably not that hard. It's mostly a matter of manpower and of money. If you would get a lot of bright people together, bright and creative people together, who can work on something that we discussed or even more futuristic ideas, you can achieve them much faster if you have really a much larger pool of talents and no monetary restrictions. And I believe that's one of the reasons why the companies that do those things for space travel, like SpaceX and Blue Origin and SpaceX, and that is because it's simply the hobby of one of the richest people here on Earth and two of the richest people here on Earth, and so they can put in a lot of money and they have a lot of manpower, and they achieve things for which NASA took much longer to achieve the same technical advantages technical progress in space flight.
Reusable rockets change the game.
Yeah.
Right. So we were talking about that last episode actually.
Okay.
Yeah. I feel like, but also like the technologies that we use in the reusable rockets aren't like that much advanced than the ones that we have before. So like, is it just like we just need to pay more attention into these fields and just throw as much monetary incentives, then we can advance? Because I also see like people think for us to go to a higher level of like, for example, moving stars, we need new ideas in physics, like how do we manipulate space-time, for example, the grav drive and all those stuff. Like how do we, like, I guess my question is, like, do you think it's possible to find a new type of physics that can do such a thing? Like,
Physics,
in a more,
yeah.
in a more, like, um, achievable way with, like, engineering applications?
I think physics is constantly evolving, and it might come to changes like that. In general, what I observed is those theories that are in physics that are very complicated and they have a lot of theoretical background and it's very hard to understand them, even if you think about them a lot of time, then that's usually something that goes away. Only the most easy physics concepts survived in the past and work for for the to explain nature around us, how things work. For example, the force equation, force is mass times acceleration, is such a simple one, and that's the one that really works and that makes a good theory. And when you hear today about theories that do this and that and combine this and that and the other things, and it's really hard. So these are the ones that will be simplified or replaced with something that much easier explains the universe, because the universe is not that complicated. If it were too complicated, it would not exist.
Oh, why is that?
Because complicated things nobody would understand, and there would nobody then thinking about them, and that's why should there be a universe when it doesn't have a purpose?
That is a very powerful way of looking at science and kind of like how the nature, the laws of things. I think that also like kind of ties into like why there's the similarities between everything, like about Legos, about stars. There is maybe a very simple rules that kind of summarize the way how world is working, the way how world should be working.
And you like see those images of like how nebulas are similar to like our eye structure, or like things like that. So like the similarities between like Earth and the universe that we just sometimes don't realize, and it's pretty.
Everything follows that mass distribution, and that shows everything is in the same universe. Everything is related with each other, because that distribution is in all parts of the universe visible, not just for stars and planets, but also here on Earth, and for city buildings in the city, and the animals on campus, and the flowers and the big trees. You can see it everywhere, and it just shows you that everything is in connection with everything else. And that's probably really the answer to that. It's just because we are all in the same universe, and because we have all the same origin in the Big Bang, and that's why we are all a big family.
We're all made out of star stuff at one point in time.
Yeah, we are made from star stuff, but not just star stuff. We are still connected with the most distant galaxy, because we see the same type of distribution in all kinds of things around the cosmos.
And if you just have 1 or 2 more minutes, just have a quick question, because I think it's closely intertwined with your research. The fate of the universe, like with the big crunch, the big rip, what's the big freeze, that has to do with mass density. And I was just wondering if we could get your thoughts on that as well.
Yeah, you could, but it's not so interesting.
It's not so interesting?
No, well, maybe it is interesting, but it depends on the question how much mass and energy has been created at the beginning of all times at the Big Bang. First of all, mass and energy is essentially the same thing. You can convert it back and forth, and the most famous equation for that is probably just the only equation that I have in my mind that I memorize. E is mc squared, which connects energy with mass. So you can convert mass into energy, energy into mass. But it's actually not just this equation. It's an equation in physics 1 that energy, kinetic energy, is 1/2 mass velocity square. You don't even need Einstein to show that. It's already in that kinetic energy equation that you can convert mass into energy and back and forth. So all the energy that was created at the beginning of all times means also all the mass that is here. And the question is how much of the mass is here, and that determines, when we know really all the mass and energy that's available in the universe, how much is the mass density, and if you can reverse that expansion of the universe or not, and if we end up in a big crunch in many years. I don't know the number right now, but we are currently in a very young universe, so the universe doesn't exist for a very long time yet, only about 14, let's say between 10 and 15 billion years. It depends on a lot of factors, and there is quite some discussion about that. But it depends on that how much mass and how much space does the current universe have, and that determines if there will be a big crunch or if the acceleration continues forever or if it stops at one point.
As a tradition for this podcast, we usually ask you a question at the end of everything, and the question is, if you had one advice for our generation, what would that be?
For your generation? No,
Yes.
I don't have a particular advice for your generation, but someone of your generation just came to my office to make up the quiz, but he was sick, so I sent him home, because you have to take care about yourself, about your health first before you do exams and quizzes. That's my today's suggestion for anybody, not just your generation.
To prioritize yourself than
Yeah,
things like that, because it matters more than this like superficial thing.
right, yeah.
Wow.
All
That's
right, well,
powerful. Thank you.
thank you for your time. Yeah.
Yes.